Okay, let's go ahead and get started on the next thing that we'd like to review, and that is the properties of subatomic particles. Ernest Rutherford, in whatever year he did it, I should have looked that up, I don't remember. But he did a experiment where he took radioactive material. All right, he had this lead block. And what the lead block was supposed to do is make sure that you only ended up with a straight beam of this radioactive materials radiating out of this source. So he was just providing a shield. And what he did, he wanted to study if there was any properties to these radioactive things that were being released from the nucleus. All right, so what he did, he took that radioactive source and he shot it between positive and negative terminals where there was some attraction or repulsion. And what he found out is that there were three distinct subatomic particles that would happen. One would go towards the positive side. It would deflect towards the positive side. One would deflect towards the negative side, and one would go straight through. He named these particles. He named the one that went towards the negative the alpha particle. All right? The alpha particle. Now, if it's attracted to that negative, then the alpha particle must have a positive charge. All right? Then, the next one he discovered was the beta particle. The beta particle was attracted to the positive terminal and deflected towards it and away from the minus. So he came up with this idea that the beta particle must be negatively charged. And then the one that went straight through, he called that a gamma ray or a gamma particle. And it was not affected by charge, so he assumed it must have a neutral charge, which makes a lot of sense. All right, now, in this process, one of these deflected at a much greater angle than the other. Based on that, Rutherford came up with the idea, and eventually it was proven, that an alpha particle is radioactive, that's positively charged, and it's pretty big. It has an overall mass of 4. And that would be the AMU, or atomic mass units, that says a proton is a mass of 1 and a neutron. So the alpha particle, being bigger, did not have as much deflection towards the positive because it had more momentum to go straight. On the other hand, the beta particle, being extremely small, and he's going to say this has a negative charge and a mass of about 0, it would deflect much more towards the positive or away from the negative. All right, and then the gamma, eventually it was proven that the gamma particle has no mass. All right, now let's apply this to a little table. We'll see how this works out. This angle's not as good, but that's okay. So what I have over here, I put the alpha, the beta, and the gamma. Let me move this just a touch. All right, it's going to be crooked, but that's all right. So our symbol, whoops, I'm off. It was supposed to be up there. So our symbol is just alpha, beta, and then our gamma. And these are just letters from the Greek alphabet. All right, the mass of the alpha particle is 4. The mass of the beta and the gamma is essentially 0. A beta particle is going to be just like an electron and have a mass that's really 1/2000th of one proton, so 1/8000th. So we're going to call that 0. Now, the energy associated with these things, alpha are considered the lowest energy. Beta is in the middle. And gamma is extremely high. All right? Then, they like to talk about this energy as far as its penetrating power, its ability to go through stuff. An alpha particle pretty much has 0 ability to penetrate. All right? Alpha particles are blocked by a piece of paper or smoke. A smoke detector works through alpha particles being blocked just by smoke. All right? The penetrating power of a beta particle is pretty low. It's greater than 0, but not very much. It would take like a piece of cardboard paper or aluminum foil or something to stop it. And then a gamma particle is extremely high. All right? The penetrating power and the energy are pretty much the same thing, as well as the bottom one here as well. So when we say high, we mean high. When we have a nuclear reactor that's surrounded by lead and cement, It's to contain these gamma rays from leaving and being energetically released. All right, alpha particle, as far as danger is concerned, can't see that very well, but this last row is danger. All right, there's pretty much none. They're not going to go into my skin and cause my cells to be damaged. Beta, pretty much the same. My skin, it's pretty good at blocking beta, and even if they get through, they're not energetic enough to cause what we call ionizing radiation, which is the dangerous part. And then gamma, they are very dangerous. They do have enough energy to go into our cells, kill things in our cells or change them, and if those cells are replicated, then we're in trouble. We call that cancer. So make sure you understand both this table, the properties of these particles, and also kind of how they were discovered through this Ernest Rutherford experiment.